its symmetry. Okay, we're up to 5. Any other characteristics? Hint, yes, there are.
Slope.
When we talk slope, right there, that is what calculus is based upon. And I know I just took it away. Don't worry, I will put the recording up. Now, when we talk slope, usually slope we're talking about a straight line. But of course, when I'm talking characteristics of graphs right now, we're not just talking straight lines. In fact, the straight lines are the boring ones. We're going to spend more time talking about the curvy stuff. But we are going to talk about localized. That's what I get for trying to... I don't know if that's spelled right or not, but I made it look like an I and an A together, so whichever one you put on your paper is right. Localized slope. And by that, what I mean is we might just look at a small box. Is anybody here colorblind? Wave at me if you're colorblind. That's right. Okay. Let's use this one. Localized slope is going to be looking at what's the slope just at that area. And that's going to be almost the first topic we talk about. It's more like the 1-point tooth topic we talk about of the year. But it's coming up soon. All right, I'm going to give you another minute to tell me your characteristics.
Maximums.
Say that again?
Like minimums and maximums of like
Perfect. That's actually the next one that was going to be on my list. So if I say mins and maxes, do you guys get what that means? So, and a function can have both. It can have just one. There's only one way really that it can have neither. But we were going to call this one a local maximum because technically there are places that are going to keep going forever. Although we're going to count those separate. We're going to have things called local minimums. Local just means compared to the points around it. And I'm actually going to change this graph. And then we could have maybe a absolute minimum, or depending on your graph, an absolute maximum. Something we're going to teach you this year, one of my favorite parts of the year, is we will be teaching you how to graph functions, complicated functions, without a graphing calculator. Without a graphing calculator and without plotting endless tables trying to get your points. It's one of my favorite things about calculus. Calculus is really going to take all the math you have ever learned in your life and connect it all, more than any class you've ever had. And one of my favorite things is what we're going through now is getting us ready for thinking about those lessons eventually that'll teach us to graph without a graphing calculator. Okay, I'm going to take over now. Some other things that I have are concavity, which is not one you've spent much time with necessarily. But concavity, and I'm going to use this graph over here again, refers to, is it concave up or concave down? And so if you can make the shape of the graph with your hand, wherever your palm is, like for that first section where I put the dark red arrow, if I've made the shape of my hand, or shape of that graph with my hand, I'd have to have my hand cupped up. that is called concave up. In this location, if I had to show it with my hand what the shape looked like, my hand would be facing down. We call this concave down. And then over here in this last section again, we have another section that is concave up. That's probably relatively new to you. It's not something you've used as much. Pre-calculus students from last year, did you talk concavity? A little bit? I know my kids talked about it a little bit, but wasn't a major focus of the year. When we get to chapter 3, it's going to be a huge focus, because that's going to be one of the characteristics that's going to help us graph without the graphing calculator. It looks like I only see one more on my list that you actually didn't have, and that is going to be what I call turning points. And turning points, technically there's two different things I can mean. Turning points, in one sense, are your minimums and maximums, because you're going from up to down. But more importantly, it's going to be the points where concavity changes. So if I had to guesstimate, probably about right here, I would call that a turning point. And turning point's not necessarily the technical term, but that's what I'm going to call it. That is something that we're going to have, we call it points of inflection in calculus, but that is going to be one of the most important points that we're going to study, is where do we go from concave up to concave down? Where's that point where they meet? Because that point is going to be a defining point on the graph later. Okay, so pull this off here, so if you're still copying things down, you can. And I'm going to give you a function. Let me write out a couple of these so that we are ready to go. And let's do one more. Okay, I'm going to cover up your screen. And again, if you missed something, it will be on a recording. So I'm going to adjust the window for this because I can see I've got some dead space. I'm not using this space over here, and I'm not using this space over here. So on Desmos, I think that you maybe hopefully know, to change the window you go to graph settings, and it tells me what my smallest x and my biggest x are, my smallest y and my biggest y. I'm going to take this from, I think -4 from what I see would be a good place to start. And it looks like I have no reason to go past 4, because all that shows up. And I just like personally, and this is just me modeling for you good math behavior, I like to see the graph as clearly as I can. So I will resize the window to make the graph fill the screen as much as I can, and get rid of the dead space on the sides or sometimes at the top and bottom, so that it gives me the most clear picture for what I need. So we just went through a bunch I used to have on my browser a extension, there it is, page marker, where I can write on this. We just went through a bunch of characteristics. So slope I'm not going to worry about, but I do want things like domain and range, mins and maxes. Are there asymptotes? Concavity. One that I'm going to add to the list that we actually didn't have is where is it decreasing and where is it increasing? Let me see if there was something else on the list that I want to include. Turning points. Turning points, I'm okay not to do turning points right now. X and Y intercepts I think would be a good idea too. And symmetry and shape. Okay, so what I want you to do, all of you, is there anybody here who's on a phone, not a computer? Everybody's got a browser, like a full screen? Okay, what I want you to do is, you see I have 3 functions here, only one of them's on the screen. I want you to just go through and identify for me what are the domain and range, what are the minimums and maximums, what are does it have an asymptote? Can you identify when is it concave up and when is it concave down? And just make estimates on that one. So, I mean, like minimum and maximum would be pretty easy. Because especially if you pull it up on your own browser. You can just come up here and click and it knows that minimum and maximum is one that you're probably going to look for. And it will tell you where that local maximum in this case is. Negative 1.414. Comma 13.657, and you can do the same thing here. For concavity, I would say something like it's concave. I always do that. Concave down. CD I'm going to use for concave down. For, I'm going to say maybe the x's that are smaller than, probably right around the x is 0. So in other words, if I made the shape of the graph with my hand, everything on this side would be concave down. And then I can see everything on this side. I'd have to cup it up to represent it. I'd call this concave up. And I know I'm using, some people still don't love using this notation, but I am going to be practicing with it. And again, modeling it for you because it is the notation you're going to want to use. And I'd say something like it's concave up for this range of x's. You'll never have concave up or down at a point. It always has to be for a range of x's to be able to talk about the shape. All right, increasing, decreasing, again, similar. Say something like it's increasing from, for all the x's less than, and what was it? It was like 1.4. Then it decreases for the x's from 1.4 to, and I'm going to let you finish that off, and then it increases again, and tell me where it increases. X and Y intercepts, you know how to do that. Symmetry, tell me just if it has symmetry, and if it does, where is the symmetry, especially the line of symmetry. And shape, this is the one that always confuses my students, like every year. When I ask you for shape, you get to make up a name. What does that shape remind you of? And I'm happy with that. Okay? You get to make shape your own personal thing. Where we're going to be technical on everything else, you get to make that up.